Well, I thought my 1400 newtons here was excessive and made several mistakes around that. And I just didn't look at these numbers carefully enough. As I said, scientific notation can be beneficial. 3.7 times 10 to the negative fourth multiplied by 3.4 times 10 to the fourth gives you 3.7 times 3.4, which is around 14. Actually, I think it's probably closer to 13, maybe not even quite 13. But I'll keep the 14 there, because remember, we're only working approximately, and the 14 actually works out with the 0.07 to give us a nice round number for the joules. Okay, for the work done by the net force, the 1 joule we end up with. So if I replace the 1400 by 14, I get 1 joule, not 100 joules, which seems a lot more reasonable to me. Okay, then same reasoning as before. We just get the right numbers. We put in 1 joule here instead of 100 joules. The 0.00026 cubic meters was correct. Actually, I think that's fairly close. When we divide this, instead of getting 8,000, we get 800. It's meters squared per second squared. In the details of that, we have the square root of 2 times 1 joule over 0.026 kilograms. Same thing we have here. A joule is a kilogram meter squared per second squared. When we divide by kilogram, we end up with meter squared per second squared. Again, dividing 2 by 0.026 gives us something close to 80, and the square root of 80 is about 9. The square root of a meter squared per second squared is a meter per second, and there's our result. Now that's actually a little higher than I would have estimated. I happen to know that this pressure would be exerted by a little over a 3-meter depth of water above this thing, about 10 feet or so. And something that falls from 10 feet, as we'll see in a while, will have the same velocity with which an ideal fluid here, if water was an ideal fluid, the velocity with which it would exit would be the same as the velocity attained by falling 10 feet. And it's a little less than 9. It's probably closer to 8 meters per second if you calculate it accurately. Remember that 14 is a little high. Okay, anyhow, this is how we analyze it. Okay, we take the excess pressure on this side over the pressure, the pressure on this side in excess of the pressure on this side, multiply that by the cross-sectional area, we get the force. Multiplying that by the 0.07 meters, we get the work done by that net force. Calculating the volume of this plug, and then hence its mass, multiplying by the density, we get the mass of the plug. Plugging that in to the work kinetic energy theorem, which says the work done by the net force is the change in kinetic energy. Since the kinetic energy of this plug is initially 0, the change in the kinetic energy will just be the final kinetic energy, which is 1/2 mass times final velocity squared. Final velocity being the velocity with which this exits. We solve for final velocity. We plug in our results, our numbers, and we get our result.